So it's kind of different how things evolve over time, I guess. All right, we do want to talk about half-lives. So, I got a demo for you. Who wants to participate in the demo? You want to participate? Okay. I want you to stand up right here. Now, I'm going to prove to you that she cannot go out that door over there. You can never leave this room. Did you know that? Watch this. Turn around, face the door. In order for her to go out the door, she has to go halfway there. Who agrees with that? She has to go halfway there. Okay, go halfway to the door. And stop. Okay? Now, to go through the door from where she's at right now, she has to go halfway there again, doesn't she? Go halfway again. You went way over halfway. Come back this way, son. Come on. All right. Now, you got to be good about going halfway. Okay? Now, to go halfway out the door again, she has to go halfway again, right? Go halfway again. No. Halfway. Half of where you're at. You got to go half of where you're at each time. Okay? Now, to go out the door, she has to go halfway again. And now you got to go half of where you're at again. You got to go halfway again. And halfway again, and halfway again. She's going to get really close to the door. She can never go out the door. Isn't that crazy? All right, thank you. So what's happening here? Now you're all confused, going, does that mean we can never leave chemistry class? That's right.
No.
Can't ever leave. I've got you forever now. You're trapped. No? No. The idea of half-life is this. Watch this. If you have 100, after one half-life, you're down to how much? 50. All right, well then it's just like you just start over, brand new. And then we'll have a second half-life. We'll be down to 25. And then we're going to start over brand new again. And on the third one, we'll be down to 12 and a half. And then on the fourth one, 6.25. And then, I don't know, we keep going. We'll be down to 3.125. Is it 125? Yep. And then we'll go down again. 1.5625. And then we'll go half again. 0.78125. And we'll go half again. 0.3906, something or other. Go half again. 0.1953. Go half again.
0.0976.
Go half again.
0.04882.
882. Go half again. 0.02441. Go half again. 0.0122. Close enough. What's happening?
It gets smaller.
It gets smaller and smaller and smaller, closer and closer and closer to zero, but it never gets to zero.
It's smaller than zero.
No, it can't get less than zero. It's less than 1. It's between 1 and 0, right? It's not smaller than 0. It's just getting really close to 0. Anybody know what the word asymptote means? You take algebra in high school, they talk about asymptote. If we graph this, what is it going to look like? It's going to look like this.
It'll get parallel.
It's going to get really close to 0,
Never touch it.
but it'll never be 0. That means you can't ever go out that door? No? Okay, that's the idea of half-life. Okay, so here's their example. Here we have iodine 131 again. We start with 20 milligrams. After one half-life, we're down to 10. After two half-lives, we're down to 5. After three half-lives, we'd be down to 2.5. Okay? So, this is called a decay curve like I drew before. Here they have it plotted. Here we have the amount of iodine versus time, and you note that it's a curve, right? And it will approach 0, but it'll never get to 0. You always have some tiny bit left. Okay? Depending on how many half-lives you go past, that's what you wind up with. So, here are some common isotopes and their half-lives. Look at these up here. They're all really long time, right? Look at uranium. What is that? 4.5 times 10 to the 9th years. How many years is that in words? 4.5 million years?
No.
How many is it? 4.5, 10 to the 9th is a billion years. Okay, so it's 4.5 billion years for half of the uranium to decay. So if you had 10 atoms of uranium in your hand, in 4.5 billion years, 5 of them would have decayed. You'd be long dead, but you would still have 5 in your hand. Because you're not going to live 4.5 billion years. Pretty sure.
That'd be awesome.
I don't think I want to live that long.
Oh my gosh, it's my best friend calling me again.
Hello.
Oh, that's so sweet.
If it rings again, can I answer?
Sorry.
That's so sweet.
Actually, the shade of red she turned is priceless. I mean, oh.
That's my best friend.
So look at all of these up at the top. They have pretty long half-lives, right? Well, in today's world, a lot of what we use radioisotopes for is medicinal issues or purposes. We use them diagnostically to figure out what's wrong with somebody, and we also use them in treatments. Well, if you're going to use uranium, and it has a half-life of 4.5 billion years, they're going to be long dead of whatever they had before you figure out what's wrong, okay? So we have to choose an isotope that has a half-life that we can measure and figure out what's going on or treat them in a reasonable amount of time. So look at all the ones down here. Here's chromium-51 has a 28-day half-life. The iodine 131 has an 8-day half-life. So you see these are in days, right? Some of them are actually in hours. Technetium-99M has a 6-hour half-life. Okay. So they all have different uses, right? Okay. So the half-life has to be a reasonable amount of time to make it useful. So let's do some calculations. Let's say we start with some strontium-90 and it has a half-life of 38.1 years. And we start with 36 milligrams. But we wait 152.4 years. How are we going to figure out how much we have left? Think about it. How many half-lives have we gone through here? If the half-life is 38.1 years and 152.4 years, 152.4 years divided by 38.1 years equals 4 half-lives. Okay? Everybody agree with that? 152.4 divided by 38.1.
Yes.
So because we've gone through 4 half-lives, watch this. Times 1/2. Ooh. Times 1/2. Times 1/2. Times 1/2. Times 1/2. So after 1 half-life, we'll be down to 18. After 2 half-lives, we'll be down to 9. After 3 half-lives, we're down to 4.5. And after the last one, we're down to 2 1/4. Round it off to 2 sig figs, 2.3 milligrams. Fair enough? Right? Take the total amount of time divided by the half-life, that tells you how many half-lives, multiply by 1/2 for each one of them. And then I'll get you there. Okay? Now this is how they also date things like mummies and stuff. In the Dead Sea Scrolls, they use carbon-14, has a half-life of 5,700 years. So it's useful for dating things on a thousands of years time scale, so you can figure out how long the mummy's been in the Peruvian cave, basically, right? Don't worry about that one. I don't worry about this fraction. But you should be able to do this. Yes.
I can't see
See
it.
that? Oh, you didn't have to
Pretty easy. So you want to vote? 1, 2, or 3, A, B, or C? Ready, set, vote. Why aren't y'all voting? Oh, we got some issues. Let's look at it. So we've gone 26 hours divided by 13. That means 2 half-lives, right? So 64 times 1/2 times 1/2. After 1 half-life, we're down to 32. After 2 half-lives, we're down
Oh,
to
just kidding.
16 milligrams left. Okay? We're all good now?
So I have a question.
Yes, ma'am.
Instead of doing half-life times half-life times half-life,
Uh-huh.
is there a simpler way to do it by doing like an exponent, like half to the 4th power or something?
You can use this equation right here. Would you rather that equation?
No.
Okay then. So we'll just do this.
Okay.
This is the easiest way. This will tell you at any point, not even necessarily the half-life, but for us, this is what we're gonna do in here. If you're gonna take 152, this is what we do in here. Okay, medical applications. Anybody know what this is? Thyroid scan, right? Anybody buy salt? Anybody buy salt at the store? What kind of? You buy iodized salt, don't you? Why do you buy iodized salt? Where does that iodine go to? It goes to your thyroid, prevents you from having a goiter. You guys probably never seen a person with a goiter before. You should look it up. It's not pleasant. It's not pleasant. Yeah, their throat's like huge. Okay? But that's why we put iodine in our salt now. Okay? But this iodine, if we inject you with radioactive iodine, it would go to the same place. It would go to your thyroid. And then you see this thing that they have right here over her neck, right? This thing right here. It's detecting the radiation coming out of her thyroid, and they can computerly generate a graph of what her thyroid looks like. Okay? So you see there's high concentrations in the middle, lower concentrations on the outside. I guess that's a normal thyroid scan. It's not what I do for a living, so I have no idea. Okay? So these radioisotopes with short half-lives are all used in medical, a lot of them are used in medical industry. Your body doesn't know, is this radioactive or not? It just uses it like it would normally use it, and so you can do different things with it. And if you can measure the radiation, it makes it useful. So here's a whole list of various ones. There's probably the total list is probably at least 10 times the size of isotopes that are used, okay? But you can see they're used for all sorts of stuff. We'll talk about a couple of them.